Right. Okay, so welcome everyone. This lecture will follow up yesterday's lecture on the continuous functional calculus, and this one will be about positive elements of the C-star algebra, which we haven't defined yet, but some initial remarks. Positive elements in a C-star algebra, they generalize non-negative real-valued functions in C0 of x for a locally compact Hausdorff space x, and also they generalize positive semi-definite operators in B of h. We'll see that they determine a partial ordering of self-adjoint elements. And we will see also in this lecture that elements of the form A star A, as you see in the C star identity, are always positive. And in fact, all positive elements can be written in this way. So positive elements will end up, we haven't defined them, but this is a definition. It's one definition you could use that they are the same as elements that can be written A star A for some C star algebra element A. But here's the definition we will use. Let A be a C star algebra. Then an element A is positive if it is self-adjoint. So we require that the element is self-adjoint. And also, if its spectrum is contained in the non-negative real numbers. And we'll denote this by A greater than or equal to 0. That's the notation we'll use. So this is a condition where we require the element to be self-adjoint, but it's also a condition on the spectrum. We want its spectrum to be non-negative real valued. So what are some examples? Again, non-negative real valued functions in C0 of x for locally compact Hausdorff space. So how do we see this? Well, let's say x isn't already compact, so it's locally compact Hausdorff. We can let x union infinity denote the one-point compactification and observe that for the unitization unit of twiddle of C0 of x, we have that's isomorphic to C of x union infinity. That's something you can check. So you can convince yourself that if you have a locally compact Hausdorff space, not already compact, the unitization will be the same as continuous functions on the um, x union infinity. And for that, you can recall that the continuous functions vanishing at infinity at of x, so C0 of x, are the same as the continuous functions vanishing at the point at infinity, the point that we call infinity of x union infinity. So C0 of x will be isomorphic to a subalgebra, isometrically isomorphic to a subalgebra of C of x union infinity, and then the unitization will actually be all the continuous functions once we send 1 to 1. So then you can note that invertible functions in C of x union infinity are the same as nowhere vanishing functions. And for that, that's a general rule that we're going to be recalling as we do this lecture. So if we have an algebra of continuous functions, well, the invertible, well, let's say it's an algebra of continuous functions of a Hausdorff space. Well, the invertible functions of a compact Hausdorff space, the invertible functions will be the same as ones that don't vanish anywhere. That's not too hard to convince yourself of, but the upshot of that is that the positive functions will be the same as ones that are non-negative real valued once it all comes down to it. So also positive semi-definite operators, t at least 0 and b of h is another example. So operators t such that the inner product of tx and x is at least 0 for all x and h. We'll prove this later in the lecture. So we see we have some different motivation for writing positive here as a greater than or equal to 0. You might ask, why are these called positive operators instead of, or positive elements instead of non-negative elements? In a lot of ways, like saying the element is non-negative would sort of fit better with the characterizations of these elements that we have. But positive, the word positive sounds better than non-negative, so that's what we use, I think. All right. So some key facts. Here I have some notes at the top to like recall what we did with the functional calculus. We're going to be using the functional calculus a lot in this lecture. So let A be a C-star algebra, let A in A be a normal element. If A is non-unital, then we may embed A into its unitization, a twiddle, and consider that B, or consider the algebra B defined to be C star of 1 and A. So the algebra generated by 1 and A, a commutative unital C star subalgebra. We can recall that in this identification, we end up being able to identify B with C of the spectrum of A, where the spectrum of A is a compact Hausdorff space. And are we working with the spectrum relative to the algebra A or the smaller algebra B? Well, we made some notes in the last lecture about how they're actually the same spectra. So um, the two spectra here will be the same. Now we identify this via the map, 1 going to 1 and A going to the identity function, where this identification also realizes the smaller C star algebra only generated by A without the unit as C0 of spectrum of A minus 0. And in this setting, we may use the functional calculus on A. So how do we use the functional calculus? Well, I mentioned this map going from B to C of sigma of A. It's an isometric isomorphism, so we can take the inverse of that map, where we send continuous functions to B, and those continuous functions are how we'll define the functional calculus. When we say f of a for a continuous function f, we're saying we took the continuous function f from c of sigma of a and we sent it over to b, and that's how that goes. So that's just some review there from the last lecture. So I have a lot of exercises in this lecture. The first one I have here, the exercises are very foundational, so they're ones that you might want to think about in the coming days if you want to do review. There's some good exercises to think about. If I happen to have any remaining time at the end of this lecture, I'll probably like rewind the slide over to some of the exercises and we can talk about them. So exercise, each positive element, A and A, has a unique positive square root. You get that from the functional calculus essentially. Actually, you have to, well, to get uniqueness, you have to establish that there's a unique, I think, positive square root in any commutative C-star algebra containing A. So anytime you have the Gelfand transform on some commutative C-star algebra containing A, you'll be able to see that its positive square root in that setting is unique. And then, so any positive square root that you have will be the same as the one contained in particular in C-star of A. And so you get a positive square root. And to get that positive square root in the first place, to show that it exists, well, it's a functional calculus thing. And that's something you'll be able to think about yourselves, I guess. But we could talk more about it. So another exercise for each self-adjoint element A. There exist positive elements A plus and A minus, such that A equals A plus and minus A minus. So you get a difference of these two positive elements. They'll also satisfy the property that A plus times A minus equals A minus times A plus, which equals 0. And my hint here is for the A plus and the A minus with the subscripts, you might recall similar notation from measure theory. If you do, you can apply the definitions you remember from measure theory to the functional calculus and see that things work out in this way. But it's good to think about like what those functions will look like in the functional calculus because this characterization of an element decomposing into a difference of two positive elements, it'll come up again. Now we arrive at an important proposition here about characterizing positive elements. So let A be a self-adjoint element in the unital C-star algebra A. Then the following are equivalent. First, that A is positive. Second, that A equals B squared for some self-adjoint B in A. Third, that the norm of for a non-negative scalar alpha, the norm of alpha times identity element minus A is less than or equal to alpha actually for all alpha, for all scalars alpha greater than or equal to the norm of A, and also that the same holds but only for some alpha. So if it holds for some alpha, it'll hold for all alpha. This is a proposition we'll be using to prove further things about positive elements. Now, the proof. Clearly, 3 implies 4. If it holds for all alpha, then it holds for some alpha. For instance, you could set alpha equal to the norm of A. Now, 1 implying 2 follows from the previous slide, since A is a unique positive square root, because the positive element in particular is self-adjoint. Now, given 2, recall that B equals B star, in other words, that B is self-adjoint, implies that the spectrum of B is an R. Then in the functional calculus on B, you can identify A with the function x squared of sigma of B. Well, that's valued in the non-negative real numbers, so that implies that A is at least 0. So 2 implies 1. Now, for 1 implies 3, we want that A positive implies that norm of alpha minus A less than or equal to alpha for all alpha at least the norm of A. So let A be positive and let alpha be at least the norm of A. Then the functional calculus on A, we have that alpha minus A. It's identified with the function alpha minus x for x being the identity function of sigma of A. And the image of that function has to be contained in the it has to be contained in the real numbers between 0 and alpha. Because it's positive and because x is just like positive or non-negative value the whole time. And so therefore the norm of alpha minus a is less than or equal to alpha. Why is that? It's because for a self-adjoint element, its norm is equal to its spectral radius. So therefore, that since that holds for all alpha, we have 1 implies 3. Finally, we'll establish that 4 implies 1, that if it holds for some alpha, then A is positive. So assume we have alpha minus A norm less than or equal to alpha for some alpha at least A. Then in the functional calculus on A, alpha minus A is identified with the function alpha minus x, again, of sigma of A, whose image, because of the condition on the norm, has to be contained in, well, has to be contained in the interval from minus norm of A to norm of A, which will itself be contained in the interval from minus alpha to alpha. This implies that there's no negative element to the domain sigma of A. That is to say that since A is at least 0. So therefore, 4 implies 1. Oh, by the way, again, you guys can interrupt me anytime or just, ask questions if you would like to. That's totally good. So this completes the proof of that. Now, a corollary of this, using the stuff about alpha, the set A, we can call it A plus of positive elements, is closed. So a corollary, let A be C star algebra, let A plus denote the set of positive elements in A, then A plus is closed in A. So proof of that, well, if A is non-unital, we can embed A into its unitization, A twiddle, and then so we have a unit in this algebra. Now let AN be a sequence of positive elements converging to an element A. Then we can set alpha equal to the norm of AN for each n, and we have this inequality. Then continuity of the norm implies that the norm of norm A minus A is less than or equal to norm of A. And that's enough because it holds for the alpha equal to us norm of A. For the element A, we have that A is a positive element. Okay, so from here we can get a partial ordering on the set of self-adjoint elements, A sub SA, which we can denote that way. Um, so exercise, if A and B are positive elements in C star algebra A, then A plus B is positive. And you can use that, you can prove that using the stuff about how A is positive if and only if we have that inequality for some alpha, at least the norm of the element. So that's an exercise that you can think about. Now, as a consequence of this exercise, one sees that the set of self-adjoint elements has a partial ASA and A, has a partial ordering via the relation A less than or equal to B if B minus A is a positive element. So reflexivity comes from the fact that 0 is always positive. Anti-symmetry comes from the fact that for all A, you can notice that the spectrum of minus A equals minus the spectrum of A, where then A, if you have A smaller than B and B smaller than A, that's going to imply that the spectrum of B minus A is zero. So B minus A is a self-adjoint element with zero spectrum. And because the spectral radius of a self-adjoint element equals its norm, that's going to imply that B minus A equals zero. In other words, A equals B. So that's how we get antisymmetry. Now, transitivity, that's provided by the previous exercise. So if you have at least A and C at least B, then we add C minus B to B minus A to get C minus A, and we see that that's positive. Okay, so some additional exercises. Let A be a C star algebra. Um, Suppose we have normal elements A and B such that AB equals BA. Then you can check that if you apply respective functions of the functional calculus to A and B, you can reverse the order of multiplication of that too, and you get commutativity. And to do this, you can start by using polynomials and show that you have the commutativity for polynomials, and then use that polynomials are dense and use some multiplicativity of the norm. Then, as a corollary to this, you can show that if A and B are positive commuting elements, then A times B is at least zero. It's a positive element, that is. There's a little trick you can do there using a previous exercise. Now, another exercise, this I think isn't in the notes, but I added it in here. Um, let A be unital and let A and A be a self-adjoint element. Then for all real numbers, lambda at least zero, we have that the norm of A is smaller than lambda, less than or equal to lambda, if and only if minus lambda is smaller than A, which is smaller than lambda 1. This is sort of smaller than lambda in the partial ordering. That's something you can check using the functional calculus. Further exercise here. Let A be unital and let A be an invertible positive element. Then the inverse of A is positive. And that's another functional calculus thing that you can think about here. Okay. So here's the theorem we're going to prove. We mentioned that positive elements are the same as positive semi-definite elements in bounded operators in Hilbert space. We're going to prove that right here. And it's not obvious. It's something that we really have to check. So theorem, given T and B of H, we have that T is at least zero, if and only if T is positive semi-definite operator. That is that the inner product T of X with X is at least zero for all X and H. So for the proof, start by assuming that T is at least zero. Then we know that T has a unique positive square root, which we can call S. Then we do inner product stuff to see that inner product of Tx with X is the same as inner product of Sx with Sx, which is the square of the norm of Sx, and that's at least zero. So we get that T is positive semi-definite. And then the harder part is going the other direction, where we start by assuming that T is positive semi-definite. Then, since inner product of Tx with X is in the reals for all X, we can do inner product stuff to see that inner product of Tx and X is equal to inner product of T star X with X, which implies that T minus T star, well, is it itself a joint? Is T minus T star, oh, wait a second. Did I make a mistake here? I think I made a mistake because if you take the star of T minus T star, you get T star minus T, which is the negative of what you started with. So I think there's a slightly different argument you have to use here to conclude that T is self-adjoint, which is the object of the slide at the bottom. It's in the notes, so there might be a slight mistake here, but the fact that T X and X inner product equals T star X and X inner product ends up implying for all X ends up implying that T equals T star. And there's some argument you can use to show that. Okay. So therefore, the sigma of t is in the reals. Now let lambda be less than 0. We want to show that lambda is not in the spectrum. So then for all x and h, we have that if we apply t minus lambda to x and we take the square of the norm, that's going to be equal to the inner product of t minus lambda applied to x with itself. And we can expand stuff out into a sum of non-negative real numbers using a bilinearity of the form. We get norm, square the norm of tx. In the sum, we get um, modulus of lambda squared times norm of x squared in the sum. And we also get, because lambda is negative, we'll also see that in the sum we have 2 times the modulus of lambda times inner product of tx with x. And that's in particular going to be greater than or equal to modulus of lambda squared times norm of x squared. And therefore, we get that when we take square roots, we have norm of t minus lambda applied to x is at least modulus of lambda times norm of x, which implies that uh, t minus lambda identity is injective. And recall here that modulus of lambda is strictly positive, so we get injectivity. Now, it's a general fact about linear operators that if we have a linear operator t, then the kernel of t is going to be equal to the orthogonal complement of the image of t star. So we have that that's true in particular for t minus lambda, which is self-adjoint. This implies that t minus lambda is also surjective. And why is that? Well, we know that the kernel of t minus lambda is 0. Therefore, the image of t minus lambda has orthogonal complement 0, which means that it's surjective. Or it at least means that it has a dense image. And then we get surjectivity because this image has to be closed, given this inequality on the norms. So therefore, the open mapping theorem will imply that t minus lambda I is invertible. So lambda is not in the spectrum. Therefore, the spectrum of t will be in the non-negative reals. So t is at least 0. That is, t is positive. This completes the proof. Okay, so we come to this fact that was mentioned previously that every element A star A is positive. We've established previously that every positive element of a C-star algebra A is expressible in the form A star A for some A, where in particular we may take A to be self-adjoint, then we're saying it's the same as like the element having a self-adjoint square root. And it turns out that all elements in this form are positive. So given any element A, we have A star A positive, and this is a bit tricky. I'm going to go through the proof though. Let A be an A and denote B equals A star A for convenience. We have by an exercise a standard decomposition of B is a difference of two positive elements. So B equals B plus minus B minus, obtained from the functional calculus on B. When you get the standard decomposition this way, you end up seeing that the product of B plus and square root of B minus equals 0, and also that the square root of B minus commutes with B. And so that's something we can note. We'll use it on the next slide. And to show that B is positive, in other words, that A star A is positive, it'll suffice to show that B minus is equal to 0, because then B will be equal to B plus, which is a positive element. Now denote C equals A times square root of B minus. We'll denote it that way for convenience. Then if we take a minus C star C, we get minus a squared B minus times A star times A times the square root of B minus. And we can write that as minus square root of B minus times the difference B plus minus B star times square root of B minus. And if we expand using the distributive property, we end up multiplying b square root of b minus by b plus, which gets us 0. We can also interchange the order of multiplication between square root of b minus and the element b minus to get that this all equals negative of b minus times square root of b minus times square root of b minus, which is the same as, or the negative of that, which is the same as the square of b minus. So we get that minus c star c is equal to the square of b minus, which is a positive element because it's the square of a self-adjoint element. Now we have the standard decomposition of C into its self-adjoint parts. So C equals the real part of C plus I times the imaginary part of C. For real and imaginary parts are the terminology we're using for the self-adjoint parts of C. We will see that C times C star equals the sum of C star C and C star, all that minus C star times C. And when we take the sum of C star C and C star, we end up being able to reduce that to 2 times the real part of C squared plus the imaginary part of C squared. We add that to B minus, or we add that to the square of B minus, since we're adding the negative of C star C. And so that gets to C star in the form of positive elements, a sum of positive elements. Therefore, C star is positive. Now, it's the general fact that given elements x and y in a complex unital algebra, we have that the spectra of x, y, and y, x are actually equal, give or take 0 complex number. Since if lambda is non-zero and lambda minus xy is invertible, then the inverse of lambda minus yx we're able to write down explicitly in this certain form. You can check that that's indeed the inverse of lambda minus yx. Therefore, C star being positive implies that also C star C is positive. So now we've shown that plus or minus C star C are both positive, which implies that sigma of C star C equals the 0 set, where then C star C equals 0. It's a self-adjoint element equal to 0. And so 0 equals the norm of C star C, which equals the square of B minus norm, which using the C star identity, that equals the square of the norm of B minus. And that gets us that B minus equals 0. So we get what we wanted at the beginning, which is that A star A equals B plus, and this completes the proof that A star A is positive. All right. So we have one more topic in this talk, and the talk might end early, in which case we'll be able to talk about the exercises and stuff. So this final topic in the talk is the polar decomposition of an element of a C star algebra. So given A in the C star algebra, we'll define the positive element, I'll call it modulus of A to be consistent with terminology from the complex numbers. We'll define the positive element modulus of A to be the unique square root of A star A. So modulus of A equals the square root of A star A. It'll follow from the functional calculus then that the modulus of A is in the C star algebra generated by A star A, which is self-contained in the C star algebra generated by A. Now, a theorem is, that for each operator T in B of H, There's a unique partial isometry, U in V of H, such that the kernel of U equals the kernel of T, and U times modulus of T equals T. Moreover, the modulus of T is in C star of T, and U is in the double commutant of C star T, which is to say that U is in the von Neumann algebra generated by T. And if T is invertible, then we'll also have that U is unitary. So if H is equal to C, for instance, we'll have that B of H can be identified with C, since all operators are multiplication operators. And this will reduce us to the usual polar decomposition, Z equals real part, or the modulus of Z times the unit circle element e to the I theta. And let's recall what a partial isometry is. So there are two equivalent definitions of partial isometry on bounded operators on the Hilbert space. So one is that U is a partial isometry if and only if U equals U star U. Another is that U is the partial isometry if it restricts on kernel of U perp to an isometry onto its image. So those conditions end up being the same, and we'll kind of use both in what follows. Now, proof of polar decomposition. For all x and h, we have that the norm of t of x squared by moving stuff around is going to be the same as the norm of modulus of tx squared. And it follows that because norms of t and modulus of t on all elements are equal, there will be a well-defined asymmetric linear map U0 from modulus of t of h to t of h, given by modulus of t of x going to tx. And this will extend to an isometric and onto a linear map, given by U0 from modulus of t h closure to modulus t h closure. We will define U and B of H such that the restriction of U to the closure of modulus T of H is U0, and also the restriction of U to orthogonal complement of modulus T of H equals 0 identically. So then use the partial isometry with the U star restricted to closure of image TH equals U0 inverse, and this follows from some general facts about partial isometries. And then we'll have a kernel U star equals the orthogonal complement of UH, which is the same as the orthogonal complement of the closure of TH. That's going to be the same as the orthogonal complement of just TH. And by definition, we'll have that UT modulus equals T. Since the modulus of T is self-adjoint, we'll have that the kernel of U equals the orthogonal complement of the image modulus T of H, which will be the same because by self-adjointness as the kernel of modulus of T. And that'll be the same as the kernel of T by the thing on the top where T and modulus of T have the same norms for all elements. So kernel of U will be the same as kernel of T, which proves the existence of the polar decomposition. Now for uniqueness of the polar decomposition, we have that modulus of T is in C star of T, by the functional calculus. And suppose that S is in the commutant of C star of T, then given X in orthogonal complement of modulus T of H, well, we have that set is equal to kernel of U, also equal to kernel of T, and we have that TSX equals STX equals 0, which gets us that SX is also in the kernels of U and T. Therefore, USX equals 0 equals SUX for all X in the orthogonal complement of the image modulus T of 8. So the restrictions of US and SU to the orthogonal complement of modulus T of 8 will both be identically 0. Meanwhile, for modulus T of X and modulus T of H, for an arbitrary element that is, of modulus T of H, we'll be able to use that S commutes with everything in C star of T to move stuff around and ultimately get that US of modulus T of X is equal to SU of modulus T of X, which means that US and SU are identically equal on modulus T of H, where then by continuity, we'll have that US and SU are identically equal on the closure of modulus T of H. So therefore, since H decomposes as an orthogonal complement of modulus T of H closure and orthogonal or has this orthogonal decomposition, I mean, into modulus T of H closure and orthogonal complement of modulus T of H, we're able to conclude that US is equal to SU, and so U turns out to be in the orthogonal complement, not the orthogonal complement, the bicommutant of C star of T. In other words, U is in the von Neumann algebra generated by T. So, oh, that wasn't for uniqueness. What was that? Oh, that was the orthogonal complement decomposition, or the orthogonal complement part that we had here. Yeah, that's what we proved here. We proved that using the orthogonal, not orthogonal complement, the bicommutant of C star of T. But we'll be able to prove uniqueness from here. So in the polar decomposition. So let V and B of H be another partial isometry with kernel of V equals kernel of T and V of modulus T equals T. Well, by definition, we have that V and U are equal on the modulus T of H so that they're equal by continuity on closure of modulus T of H. Now we have this chain of equalities, kernel of V equals kernel of T equals kernel of modulus of T equals orthogonal complement of modulus T of H, which also equals the kernel of U. Therefore, V and U are both identically 0 on modulus TH perp. Thus, since H decomposes as an orthogonal complement of modulus T of H closure and or H has an orthogonal decomposition into modulus T of H closure and perp of modulus T of H, we have that V equals U. So the partial isometry U in the polar decomposition is unique. Now finally, suppose T is invertible, then we have that T star T is invertible, which implies that the square root of T star T is invertible, which you can check using the functional calculus, I'm pretty sure. This provides that U equals T times the inverse square root of T star T, which is self-adjoint, where inverse square root of T star T is self-adjoint, in fact, positive, following, I think, from maybe an exercise. Yeah. So here we obtain, well, what is U star U? It'll be, well, when we write U star U down, we can write it in terms of the equality U equals T times inverse square root of T star T above, We get a t star t in the middle, which we can interchange the order of multiplication with for t star t inverse square root. We end up getting inverse of t star t, which equals the identity. Now for u times u star, we'll have t times square of t star t um, inverse square root and multiplied by t star. We can do a trick where we multiply the right-hand side by t times t inverse, which gets us the same thing. Things cancel out when we do that to get us the identity. And so in the case that t is invertible, we get that u is a unitary. Finally, a polar decomposition of t star. We'll leave us with a note here about that. Let u modulus of t denote the polar decomposition of an operator t. Then by general properties of partial isometries, we'll have that u equals u star u, where u star u is equal to projection onto closure of modulus t of h. That's the source projection, and also that u star equals the projection onto closure of th. That's the range projection. We'll have the corollary from the previous stuff here that t star equals u times modulus of t times u star, and that the polar decomposition of t star is given by t star equals u star modulus of t star. So proof, if A is at least 0 in a C-star algebra, then all elements of the form B times A times B star are positive. Why is that? That's something that you can check. Therefore, we have that U times modulus of T times U star is positive. And we're able to use here that U star U equals the projection onto the image of modulus of T closure to get us that if we square u modulus of t u star, we get a u star u in the middle that cancels out. We get u times modulus t squared u star, which gets us that the square of u modulus of t u star equals t star. And since u modulus of tu star is positive, we get that u modulus of tu star is the unique square root of tt star. That is, it's equal to the modulus of t star. We'll then obtain that u star t modulus of t star equals u star u times modulus of t equal times u star. The u star u cancels out because it projects onto the image of the closure of the image of modulus of t. That gets us that what we started with is equal to t star, and this completes the proof. I have one final slide here with an additional proposition about the polar decomposition. So proposition, let T and B of H with B with polar decomposition, T equals U T modulus. Then for all R linear operators in the C-star algebra generated by modulus of T, we'll have UR is in the C-star algebra generated by T. Moreover, U star US will be equal to S for all S in C star of T. Now for the proof of this, we can observe that so you can start by observing that the condition UR in C star of T holds if R is a polynomial in modulus of T with no constant term. If we get that, then we can use that U modulus of T equals T to get that things end up being in C star of T. The result that UR is in C star of T for all R in C star modulus of T follows because such polynomials are dense in C star modulus of T. So we can use an approximation argument there and closure of C star of T. Now a similar argument using polynomials in T with no constant term shows that u times u star times s equals s for all s in C star of t. And here we use the fact that u equals u times u star u. Now that's my last slide. That I guess ends my talk. And since we have more time, we can talk if you want about exercises that I mentioned previously. I guess I could stop recording. All right.
So when we prove that A star is